inspired and at least you're kind of interested. So I don't think I need to introduce myself. So I'm aware that not everybody is an engineer here in the room. Before we delve into this presentation, I want to bring us all on the same page. So what are connections actually? Structures, what are joints? What do we mean by this? So connections are critical points where structural elements meet and transfer nodes. And we may, for example, have a connection between a beam and a column. And connection can transfer different type of loads. We may have tension, shear, or for example, bending. So why connections are important? Why am I here talking about connections at all? The connections happen to be critical failure points in structural collapses, not always, but quite often they are. And connections can cause a structure to collapse due to poor design, so connections that are not strong enough, too brittle, or not stiff enough. Lack of environmental protection, so we may see corrosion in metals like steel, or degradation in bio-based materials like bamboo. And poor workmanship, so lack of skills, that's a big problem, and cost savings. So, for example, why do 10 screws if we can save and use only 2? So that means that in many collapses, connection failures are the root cause, and even when the structure elements themselves are well designed. What this means in practice is that imagine that you have two shorter bamboo poles and you want to create a longer element. So you connect them at the ends, and now you want to pull those poles apart. So it's not just the bamboo strength that is relevant, it is the connection strength that has to be as strong as the bamboo itself if you want to utilize the bamboo tensile strength in that case. So 2 more slides before we go into bamboo, I promise. This slide shows a tragic example of the importance of connections in structures. So in 1981, in a hotel in the US, 2 suspended walkways collapsed, killing over 100 people. And in the original design, the walkways were supposed to, they were supported by a single continuous rod in the connection. But in the as-built solution, there was a slight change, and suddenly 2 rods were used. And this small change caused doubling the force of the connection, and it was to a massive loss of life. And another example of the importance of connections is a collapse of a bridge, and here 46 people died. And this is an example of the importance of the environmental consideration in your design. So this was due to stress corrosion cracking, which is a form of steel corrosion. Okay, let's talk about bamboo. So connections in bamboo are quite tricky. So we engineers like to work with blunt surfaces and square corners, and bamboo has got none of those. It's round and hollow. The walls are relatively thin, about 10 millimeters, and there's not much material for the connector to engage with. And it's not uniform in size, so it's not perfectly round, it's tapered, it has nodes, and the nodes are not the same distances, etc. And on top of that, bamboo splits, it cracks very easily. That's because the fibers in bamboo run in only one direction. And if you imagine, if you're trying to insert a fastener into any type of fastener into bamboo, it's very likely to be split because you're effectively pulling those fibers apart. And it's not just the load, the stress that causes the cracking. It's drying itself that actually can cause bamboo to crack. And this particular bamboo pole has been sitting on my desk in the UK for the last 5 years. And every winter I see it cracking even more. So what happens is that in cold countries we have to use heating in winter, and relative humidity gets it's about 40%. And bamboo just doesn't really support slow humidities. It depends on the species, of course, but this one particularly is also so it just keeps cracking year by year. So there are various types of connections, and this is a very non-exhaustive list. of just a few examples really. We may see more traditional connections, more carpentry types, where like smaller bamboo is bearing on the bigger one. You probably have seen latch connections, very typical connection type, very often used for scaffolding. And there are more modern connections using steel elements. Very often those connections are made for the bespoke projects, so they tend to be quite expensive. And then there is this the connection on the bottom left. It's a very typical connection that I will talk a little bit more about. So it's just using steel bolts. And there's kind of a good source of inspiration if you'd like to see what other clever people came up with in terms of connections. There's again a non-exhaustive list in the latest version of the ISO code, and that's the International Design Code for Bamboo, and it gives us some example of possible connections. But again, they all have advantages, but there are all issues. Very often those connections are quite intricate, not that easy to actually make aside, or maybe quite expensive because of the elements that are used. So I want to focus on dowel connections. This is the most typical type of connection being used in bamboo. And so what do we mean by this? It's basically connections using a dowel. And the dowel can be bamboo itself, it can be wood, or most commonly steel. So connections that use, again, it's the same picture we saw before, steel bolts. And the interesting thing about this connection is that it's not just the bolt, it's the mortar infill inside the nodes. So we use that cement mortar to kind of compensate for the lack of material. So like with wood, we would have a certain section with bamboo because it's hollow. It's quite there's not much thickness for the passenger to engage with. So we compensate with the use of cement mortar inside. And here are some pictures that I took in Colombia of this type of connection. And again, it may look a little bit different in the Philippines, but this is kind of how they do it in the place that I visited. And the cement is not always there, it kind of depends on the strength and how strength you want your connection to have. But without that, it's very likely that it might split and actually get a lot of this. And you can also see how that mortar is being inserted into the internal, so there's that hole in front and so if you're a designer or engineer and you'd like to actually design this connection, there are two places where you can go. There's the national Colombian standard that we already heard before about, and there's the ISO. So the national standard is very restrictive. It only applies to one species, the one that is commonly grown in Colombia. It's prescriptive also in a sense that it only works with specific sizes of the bowl and the bamboo itself, while the ISO is much more versatile. So you can kind of play with your connection, and you can play with the geometry more. It gives you many more possibilities to kind of adjust that connection to the needs of the project. As long as you know the material properties of the species that you're working with, you can use those equations. And so the problem with bolted connections, is there any problem with those bolted connections? Well, since I have a slide, there probably is, like with any kind of connection for that matter. And it's the cement really, and why is it a problem? It's not always a problem, but there are kind of a few things about cement. It can, first of all, because you add it to the inside of the node, and if you've got quite a few connections in your structure, you may find that it adds to the weight of your structure, and the weight then adds to the requirements for the foundations. So the cost is higher. It may be the time that it takes for the cement to set. It may be that it's not available, although availability normally is not an issue. But the one big thing about cement is its environmental impact. Cement has high embodied carbon, which means that in the process of making cement, there's quite a lot of carbon released to the atmosphere. We know all about climate change, and we don't really want any carbon releasing carbon, even more carbon. So cement is being made by using very high temperatures, and to create this energy, normally it's fossil fuels that are being burned, and they release that carbon to the atmosphere. And on top of this, cement, when it's being heated, when it's being produced, there's a chemical reaction happening, and that also releases carbon to the atmosphere. It's about 50% of the whole emissions carbon in the cement production come actually from the process reactions. So that chemical reactions happening. So that's kind of the let's say the issue with this typical connection method, and we're kind of trying to find different ways, different connection types of maybe we don't have to use that cement. So what about screws? Screws are very commonly used in timber structures. So we're talking about screws that are we don't like wood screws because they're you cannot really use those screws to drill through steel. However, there are different types that you can, but kind of this piece of research focused on the screws that can be used for wood. And so I did my PhD in this, so this is kind of a little bit about those lab tests, the experimental testing. So I did around 250 tests with different number of screws, and those tests were done in a I have to leave the microphone. Okay, so I used different number of screws, and the tests were done in shear. So it's a kind of lateral loading of the connection, and I use different arrangement of the screws. So we can have them in line along the fiber diversion. Probably not a good idea, as we will see in the next slides. And we can also have them staggered, so having them on different fiber lines. I use different steel plate thicknesses, thinner and thicker, to see how it's the impact of that. And different materials, so we may have typical screws are made of carbon steel, and the problem with that is that in the process of making the thread, the hardening process makes the screw a little bit brittle, quite brittle actually. So depending on the design, as we will see, it actually may be brittle, and we don't really want brittle failures. And stainless steel, it's a little more expensive. It's very ductile, so it's very good for ductility, and has good corrosion properties. So I also tried this, and different head types. So we have flat head and the kind of triangular shapes, so cumbersome head, and different diameters, but we are still talking about relatively small screws. So we saw different failure modes of those tests. Basically, depending on the geometry, the properties of the connection, it can fail in different ways. So unsurprisingly, if you have screws in one line, as I said, if you're trying to insert the fastener into bamboo, you're effectively pulling the fibers apart, which is very likely to cause splitting. However, you may say, oh, why did you actually test it if it's so obvious? We still want to kind of know the baseline and understand what is the impact of spacing, for example. So it's still good to test it. We saw some bearing and withdrawal failure. This is, as we will see, it's a very good failure mode because it's very ductile. It kind of happens slowly. And we saw some instances of screw failure. So as I mentioned, carbon steel can be quite brittle, depending again on the geometry, on the steel thickness plate. And before I talk about the strength of this connection, two more important things is stiffness and ductility. So stiffness tells us how much force the connection is taking as it displaces, and it's important in structures where it's important in any structure because stiffer elements in your structure attract loads. So if your connection is not as stiff as you thought, the load path may be different, and the loads will go to a different part of your structure. So you may get failure in a different place. So what I saw here is that the head is probably the most important factor. With the countersunk head, if it's like the blade is countersunk, then the head can rotate, and that we also found that the more screws you use, the stiffer the connection is, which is a very promising finding, because we are thinking of using not just one screw. You will never use a connection with one screw. The connection will definitely have multiple screws. So the more we can add, the more stiffer it will be, which is a good thing. And ductility. Another thing, important thing, apart from stiffness and strength, is ductility. And ductility tells us how much the structure can deform before it fails. And that's very important because it gives us a warning. It's like a warning sign for the occupants, let's say, of the building, so that they can react. And so the ISO that I mentioned gives us some like minimum requirements. I don't want to go into details about the ratios, but basically what I saw is that we can easily exceed those requirements using good design principles in schools, so having them staggered, not in one line. And just to kind of, as we can visualize really why this is important, if you imagine if you're in a room and you're looking at the ceiling and then there is a beam that is deflecting. So you see it like every day that it's deflecting a little bit, you have some time to react, while imagine that the same beam doesn't deflect at all and just suddenly it breaks. It's probably too late to act to escape. So it's a very important thing, a consideration in the design. And as I mentioned, stainless steel is much more ductile than the carbon steel, so you can kind of easily get good ductility with stainless steel. It kind of comes at a cost, because first of all, it's more expensive, so it's a cost. But also, there is a risk of corrosion with stainless steel, even though stainless steel is good inherent corrosion properties, but if you use it in conjunction with carbon steel, you may get a galvanic corrosion, so it's something also to consider. So about the strength, we talked about stiffness, we talked about ductility. What about the strength, kind of the most important thing about the design? So there's quite a lot of this slide I appreciate, but kind of what I want to say here is that, interestingly, we found that we can use existing models for timber structures. So those equations that are shown here, they are from Local 5, which is a very common design standard for timber. And I was able to actually use those equations, exactly the same equations, only using bamboo material properties, and this would give us a relatively good actually design fit. So again, it's a very good use for bamboo in general, but also for this particular connection. It gives us some kind of certainty that bamboo can be modeled using existing methods, so we are not really so lost in the understanding. We actually have a lot of understanding already about bamboo. So the kind of key insights maybe from this is that you should never really have screws in close to each other in one line, let's say fine line, so like one above the other, because that's very much cause fracture. We don't really want fracture, it's a very brittle failure mode. There's no ductility, so there is no time to escape. The good practice is to have the screws staggered, so we don't really have any two screws sharing the same fiber. This is likely to give us good ductility. If you screw staggered and you use a relatively thin plate, you are likely to see screw withdrawal, which again is a very good failure mode, because it's very slow, so there's a lot of ductility. And if you use a thick plate, again it's a good failure mode because you have this screw bending, and that's again it's a very slow failure mode. So you can see we do see a lot of ductility. The kind of gray zone when you are let's say in a risky zone is where your plate is not really thin and it's not really thick, it's somewhere in between. And I didn't mention this, but this kind of thin and thick, it comes from the Eurocode 5 names, and this is in relation to the screw diameter. So when you play this kind of this gray zone, what happens is that there is not enough plate thickness to cause substantial screw bending, so you won't get a lot of ductility. But there is enough thickness of the steel to prevent the screw from rotation and withdrawal. So again, you will not get the ductility from withdrawal. And what happens is that the screw bends a little bit, gives a little bit of ductility, probably not enough, and then it just fractures in a very this is specifically relevant for carbon steel schools, which is the typical type of school. So, location of the school, this is the most important really thing if you're ever thinking of designing using schools in the Bamboo. I want to focus just a little bit on fracture as well, because this is really a key problem for Bamboo in general, but it's also for connections. So until now we talked about the parallel loading, so that's the F parallel on the slide, and I want to talk a little bit more about what happens if you load it in the other direction, in that perpendicular direction. Kind of, maybe you've seen it if you've seen any Bamboo structures. Quite often they use like steel clamps on them, and they are normally located near connections. And there are kind of two uses of those clamps. One is to prevent the splitting, the cracking from happening. So that clamp, you can tighten it, and it will introduce the compression loads on the Bamboo. And the other use is the kind of post mitigation. So once the crack happens and you don't want the crack to progress anymore, you can also use a clamp to introduce those compression stresses onto the Bamboo. So those were the tests done at another university in the UK, Coventry University, by a student, and we looked kind of in those tests, and if we can get some kind of equation or a prediction model. Surprisingly, we did that, and it was quite a good model. It's quite accurate, and again, it uses existing timber design. So it's not anything new. We are not reinventing the wheel here. We are using existing models. We adjust them for the Bamboo. So in that case, the geometry is a very important thing because it's very different from timber. So taking into account the geometry and the Bamboo specific properties, we actually got a very simple equation that predicts the capacity, it's like fracture, the splitting capacity of this connection loaded perpendicular to the fiber, and it's a very simple equation just using the thickness and the diameter of the Bamboo. So to finish off, like to show an example of how this connection could look like, but also how it compares to this traditional connection with the bolt and mortar. This study about the bolt is from Professor Corial in Colombia, and so they did a bunch of tests on typical connection, and they found that the mean kind of the average strength is about 20 kilonewtons. So if we just keep this number in mind, 20 kilonewtons. So if you wanted to match this strength using the screws, you would need 6 of them, 6 screws, 4 millimeter diameter, which is kind of typical diameter used in timber. 6 of them on either side of the Bamboo. So there's another blade on the other side that you cannot see. So this is matching strength. Now, what about stiffness and activity? So stiffness is that K-cert, the second one. And what we see is that Bamboo has at least 30% more stiffness, likely much more in terms of tested. The kind of 30% more is based on the test that we did on the first screws. And in terms of activity, that's the last line, we can get much higher activity in the screws. And again, this is like great news. It seems like we are actually on something. So that's the loading parallel fiber that I talked about for most of this presentation. What about the load that perpendicular load? So this is the tricky one. So that study I mentioned, they found it's about 10 kilonewton the capacity. So with screws, we can only get around 5, and the reason is that at the moment, as long as the screws are near the center line of the Bamboo, you cannot really play the number of screws. It's just one crack line, and it's just a 5 kilonewton that we can get. There are a lot of assumptions here. Maybe it's 4, maybe it's 6, but it will be quite difficult to get it to 10 without more research. So this is really that really highlights the need for more research. It's not like this connection cannot really be utilized in this direction. It's just that we have to think about this strategically, placing the screws, and then again this requires tests, funding, time, labor, etc. So all this kind of research programs in the if you'd like to kind of know more about this or like see the proper guidance, and just like this was like a very on the surface I talked about this work, but actually everything that I talked about has been published in the Structural Engineering, which is a magazine for practicing engineers in the UK, and it's available online, I believe. And but also why I'm saying this is the interesting thing about this is that this is based in the UK, this magazine, and is read mostly by, I would say, UK-based engineers. And we don't grow bamboo in the UK. We don't have any structures, permanent structures made of bamboo, and yet they were interested in actually publishing this, which I think it really highlights that it's really a good time for bamboo, not just here in the Philippines, but even in places where it doesn't grow, and it's probably years, it will take years until actually bamboo is used in Europe. But I'm very excited about this because I feel like if I want to learn, if there's a demand, the supply will follow. So I think it's just we need to start this in Europe, and I'm hoping to see more guidance, more funding, and more people interested really in bamboo. And so what next? There are still issues. Fracture is a really big issue. We need more funding, we need more research to understand how we can mitigate against it, what we can really do to fracture not happen. So the practicalities of how this connection would actually look like. There are various ways that you can have steel plate screws. You can, if you're a designer, you might have really much better ideas than this. And other uses. So interestingly, because we saw really good stiffness in this connection, I thought of what about the composite actions of having two bamboo connected together and then used as a beam. And we did some tests with a student in Bristol, and it seems that that stiffness really helps, and we see much higher composite action compared to that typical connection with bolts. I'm not saying we're there yet, but it's just kind of, it's better. So it's again, it's kind of good news. And I think that's my last slide, so thank you very much.